Welcome to an introduction to text-to-image AI models. Text-to-image AI models are advanced machine learning systems that convert textual descriptions into visual images. Let's see how the process works. Starting with a text description like a sunset over mountains, the model processes this text through neural networks and then generates a corresponding visual image. These models represent a breakthrough in artificial intelligence, allowing users to generate images simply by describing what they want to see. The process involves complex neural networks that have been trained on millions of image-text pairs. This training enables the models to understand the relationship between language and visual elements. Most modern text-to-image systems use diffusion models as their core architecture. Diffusion models work by gradually adding noise to an image until it becomes pure noise, then learning to reverse this process. In the forward diffusion process, we start with a clear image and gradually add random noise. The real magic happens in the reverse diffusion process. Starting from random noise, the model progressively removes noise while being guided by the text prompt, eventually forming a coherent image. Popular models like DALL-E 2, Midjourney, and Stable Diffusion all use variations of this diffusion approach. All these models follow the same fundamental principle. They add noise gradually to images during training, then learn to remove that noise step by step while following text guidance during generation. Text encoding with transformers is the first step in the text-to-image generation process. The process begins with a text prompt that describes the image you want to generate. This text is fed into transformer-based language models like CLIP or T5. These transformers convert natural language into numerical representations called embeddings. These embeddings capture the semantic meaning of the text, including objects, attributes, relationships, and style descriptions. The quality of text understanding directly impacts how well the model interprets your prompt. A more detailed and specific prompt provides richer semantic information, leading to better image generation results. To summarize, transformer-based text encoders convert your prompts into rich numerical representations that capture the semantic meaning of your text. The quality of these embeddings directly influences how accurately the AI interprets your creative vision. The training process of text-to-image models involves several critical components. Text-to-image models require massive datasets consisting of millions of image-text pairs. Each pair connects a visual element with its textual description. During training, the model learns to associate textual descriptions with visual features. The neural network processes text inputs and attempts to generate corresponding images. The model then compares its generated output with the actual image, correcting its internal parameters through a feedback process. This training process requires significant computational resources, often using hundreds of GPUs running in parallel for extended periods. Training a high-quality text-to-image model can take weeks or even months of continuous computation. As training progresses, the model's ability to generate accurate images from text descriptions improves, although with diminishing returns over time. The extensive training process, while computationally intensive, is essential for creating high-quality text-to-image generation models. The generation process of text-to-image AI models follows a methodical approach of iterative refinement. The process begins with a text prompt that describes the image to be generated. Unlike other generative approaches, diffusion models start with completely random noise. The text prompt is encoded into an embedding vector that will guide the denoising process. The generation process then follows a step-by-step approach, typically requiring between 20 to 100 iterations. At each step, the model uses the text embedding to guide the denoising, gradually transforming the random noise into a coherent image that matches the text description. The number of steps significantly affects both the quality of the generated image and the time required. Fewer steps are faster but produce lower quality results, while more steps yield higher quality at the cost of longer generation time. This iterative refinement process is the heart of text-to-image diffusion models, transforming pure randomness into structured, meaningful images that reflect the input text. Modern text-to-image AI systems go far beyond simple text prompts, incorporating sophisticated conditioning and control mechanisms. These models can be guided by various conditioning inputs beyond just text. These include image prompts for style reference, spatial layouts, depth maps, and segmentation masks. ControlNet is one such mechanism that allows for precise control over the generation process. It takes both a text prompt and a conditioning input like a sketch or edge map. ControlNet enables applications like edge-guided generation, human pose control, and depth-aware image creation. These mechanisms ensure the output follows specific structural guidelines. In-painting is another powerful control mechanism that allows for targeted modification of specific regions in an image. Users can define a mask area where new content will be generated. These control mechanisms enable precise editing of images, targeted style transfer, and exact layout control. They give users unprecedented control over the AI generation process. By combining these different conditioning and control mechanisms, text-to-image AI models can produce highly customized and precise outputs that meet specific user requirements. Despite their impressive capabilities, text-to-image models face several significant challenges and limitations. Text-to-image models struggle with several categories of challenges. Let's explore these limitations in detail. These models struggle with complex compositions and spatial relationships. When asked to place objects in specific arrangements, the models often misplace elements or create unnatural compositions. Text rendering is another significant challenge. Models often generate garbled or nonsensical text within images, making them unsuitable for creating content with readable text like posters or book covers. Counting is surprisingly difficult for these models. When asked to generate a specific number of objects, they frequently produce the wrong quantity, even for simple requests like 4 circles. Physical inconsistencies are common in generated images. Models often create objects with impossible properties, like floating items that should be affected by gravity, or structures that could not exist in the real world. These models inevitably reflect biases present in their training data. When training data contains stereotypes or unequal representation, the model learns and perpetuates these biases in generated images. Without proper safeguards, these models can generate inappropriate, offensive, or even copyrighted content. Implementing effective content filtering systems is crucial, but remains technically challenging. Researchers are actively working to address these limitations through improved architectures, better training data, specialized fine-tuning, and incorporating human feedback loops. As these challenges are gradually addressed, the capabilities and reliability of text-to-image models will continue to improve, making them more useful for a wider range of creative and practical applications. The field of text-to-image generation is evolving at a rapid pace. Recent advancements include multimodal models that can handle text, images, and video simultaneously. Models have significantly improved in generating higher resolution, more detailed images. Modern models have vastly improved their ability to understand and follow complex, detailed text prompts. Artists and designers now have unprecedented control over the generation process, including composition, style, lighting, and viewpoint. Models like DALL-E 3, Midjourney version 5, and Stable Diffusion XL represent significant improvements in image quality and prompt adherence compared to earlier versions. As text-to-image AI continues its rapid evolution, these advancements are opening new possibilities for creative expression and practical applications. Text-to-image AI has revolutionized multiple industries with its ability to generate visual content from simple text descriptions. The applications of text-to-image AI span across numerous industries. Looking ahead, several exciting developments are on the horizon for text to image technology. These include real time generation, text to video capabilities, 3D model creation, multimodal integration, and seamless integration with creative tools. As these models continue to improve, they will transform how we approach creative expression and visual communication. These technologies will increasingly become powerful tools for creative expression and visual communication, changing how we translate ideas into visual form.